Hello and welcome to the fourth unit in the Physics 4C Physics course. And we're looking at hydraulics and pneumatic systems. And the first lesson we're looking at today is properties of fluids and pressure. Your learning goal today, I want you to be able to explain to me the properties of fluids and identify associated units that come with fluids and pressures. So, as you can see, I have a bunch of definitions that it's the same thing as before. We need to have common terminology here so we understand the lesson as we go through. So quickly, definition, what's a fluid? A fluid is a substance that flows and takes the shape of its container. All right, so fairly straightforward, but that's kind of the official definition. Hydraulics. Hydraulics, it's the science of properties of liquids. So there is an entire field dedicated to hydraulics and pneumatics, and you can go to either a university or a college program and get a degree in that. Pneumatics is the science of properties of gases, and they go hand in hand. There's relationships there, and often you kind of are dabbling in both. So hydraulics, science of liquids. Pneumatics is the science of gases. What is a hydraulic system? A hydraulic system is a mechanical system that operates using a liquid under pressure. All right, so it is a mechanical system, and we talked about mechanical systems in Unit 2, but they're operated with liquids under pressure. And a pneumatic is the same thing, except it's under a gas under pressure. All right, so there are common definitions for the pneumatic system. At the bottom of your note there, I have some examples of hydraulic and pneumatic systems. So we have a syringe or a needle. All right, a syringe is a perfect example of a hydraulic system. The jackhammer, okay, another hydraulic system. All right, for construction purposes. So these are common ones that you'd be able to identify with. We have a hydraulic jack for lifting vehicles, change tires, and so on and so forth. And probably one of the more important ones for us as a society is our brake system on our vehicles. Our brake system is a hydraulic system that allows cars to come to full and safe stop. And there's just a couple, and there's many, many more that we can talk about. All right, but those are just a couple, kind of get you in that mindset. All right, so on the second page of this note, talk about density and compressibility. So density is the mass per volume of substance. All right, so that takes you way back to your grade 9 course. And in grade 9, you taught the formula for density. Density is, we use capital D, is equal to M over V. So M is your mass, and V is your volume. All right, so there is your formula, and you can rewrite it in whatever form. At this point, I'm just going to leave it there. So there's something that you do want to make sure makes it on your formula sheet, because you will need it a little bit later on. All right, recall kinetic molecular theory. Okay, so just quickly here, I'm going to create or draw myself 3 flasks. And in those 3 flasks, I'll just reiterate your 3 states. So for a solid, what would happen is if we dropped a solid in the flask, the particles, this goes back to Unit 3, we talked about the kinetic molecular theory. So a solid would just plunk in the bottom. It would be like putting a sugar cube inside the flask. It would maintain its original shape. Then we would have our liquid. So if we drop the liquid in there, the liquid would go in, and you'd have many particles that would have looser bonds, but the particles would spread out and fill that entire flask. And then finally a gas, the difference is it's the density of the particles. So it would spread out as well, but in order to fill the flask, we need much less molecules or less particles. All right, and that's why these two are closely related when we talk about when we talk about pneumatics and hydraulics. These two are closely related because they have similar properties, and really a liquid is a form of fluid for us. All right. So a quick example here. Liquid has a density of 789 kilograms per meter cubed. So density is 789 kilograms for every cubic meter of the material. We want to know the mass if I know the volume is half a cubic meter. All right, so just using our formula, and we can practice rearranging it. I want to get mass by itself. So again, multiply both sides by volume. Density multiplied by volume is mass. So 789 multiplied by 0.5 would give us our mass. Our mass would equal, and you get a total of 394.5 kilograms in your therefore statement. Okay, so there's your density calculations. Now I did say the topic in here was density and compressibility. So now let's talk about compressibility for a second. Compressibility is the ability of particles of a substance to be pressed closer together. So what we're going to do here, let's draw kind of a pop bottle shape. And I'm going to need 3 of those in total. We'll arrange them like this. So in the first one over here, we're going to talk about a liquid. All right. So if I put pop inside here, or water, it'll spread out, and you'll fill this up right till the entire volume is filled. So my question now is, can you put more water in this particular bottle? So there is a maximum volume here. I can't go over, if this is a 2-liter bottle, I can't go over 2 liters. I can't force more liquid in. All right, can't force more liquid in. All right, so water has a very high, or it takes a lot to make it more compressible, and you just can't do it for this particular situation. Now, if I talk about some air, for example, if I open the cap, this bottle would naturally fill with air. Okay, what would happen, or can I put more air in the bottle? And in order to do that, I would have to increase the pressure, or put it under pressure. So increase my pressure. If I increase the pressure, the particles are forced closer together. And the answer, if I had a large enough pump, I could force these air particles closer together until my bottle exploded. Okay? So the gas particles can be forced closer together. All right, and that's why you get your propane tanks, you get your air cylinders and stuff like that, because we can put more gas into a container by increasing the pressure, because you can force those particles closer together. All right, so that's when we talk about compressibility. All right, liquid, not easy to compress, whereas a gas is much easier to compress, so you can make it so that you can put more of that gas in the cylinder. All right. Next, we're talking about pressure. So pressure is the magnitude of force per unit area. So my units here would be newtons per meter squared. And that's what we call a Pascal. All right, a Pascal. Pascal's the one that did all the calculations, and that's why it's named after him. And more commonly, we use kPa for kilopascal, because it's usually a larger magnitude order that we're actually measuring here. So the formula, capital P for pressure, force divided by area. So we have force, we have area, and we have pressure. All right. So there is another formula to add to your cheat sheet or formula sheet. So we need it a little bit later on. So in order to compare or talk about pressure, let's talk about the pressure on snow for a 100 kilogram person. So that's about 220 pounds walking on snow with boots. Okay, so we're going to walk on it with boots, and then a little bit later you try it on with snowshoes. So with boots, we know the formula: pressure equals force divided by area. Your force, using Newton's second law, is the mass multiplied by gravity divided by my area. There's two shoes, and my shoes cover an area of 0.03. So if we calculate that out, we end up with 16,350 pascals, or 16.4 kilopascals. All right. All right, now let's look at the snowshoe. So the snowshoe, same formula. Pressure equals force divided by area. The only thing that changes in our formula is our denominator, because the area has changed. Snowshoe's a much larger area. So if you go out to walk on snow with your snowshoe, what's happening is, because you have a larger surface area, the force of your mass is being distributed over a larger area, reducing it to 2,452.5 pascals, or 2.5 kilopascals. So when you make that comparison, it's really an eighth of that of the pressure. So you don't. That's why you don't fall through when you have snowshoes on. So therefore, the snowshoe reduces pressure to 1/8 of the shoe. All right, so that larger area, the larger surface area, the more the pressure is spread out. That's why they say in quicksand, for example, you want to kind of lay out flat, because that surface area, there's less pressure pulling you down. Not that it's really going to matter if you're in the quicksand, unless someone's coming to save you. But anyway, the larger that surface area, the less likely you are to fall through the surface, and that's why we have those snowshoes. All right. Rather than rush through, I'm going to finish the note in the next short video. So we'll see you in a second.